Okay, so today's lecture is going to be a lot of review from grade 11, but I'm going to throw in a couple of things in here that are going to stretch the ideas from grade 11 into some more grade 12 material. In particular, you may not be totally familiar with the difference in sums of cubes, and I'm also going to cover something called rationalizing the denominator today, which is a very important tool that you'll have to use in this course and the next. So to start off, let's just warm up a bit using a couple of examples that don't really require too much new stuff. So the first tricky one is, okay, I say first tricky one, but really these are all tricky in their own way. So a to the 4 minus b to the 4, okay? And I want to factor this. So give it a try, and keyword here is I want to factor this fully, okay? And that's how we're going to do all of these. We're either going to be factoring fully or we're going to be expanding fully. And I'll tell you which ones we're going to be expanding. So this one I want to factor fully. Give it a try yourself and see if you can come up to the answer. Okay, so what we want to do here is get this into like a bracketed form. The first thing that pops out at me is that we actually have a difference of squares here. So I mean, these aren't 2's, so where did the squares come from? Well, it's easy to see if you just rewrite a to the 4 as a squared squared, and b to the 4 as b squared squared. Then it becomes immediately clear. You just apply the difference of squares formula, and you get a squared minus b squared, and a squared plus b squared. Okay, are we done? No. This is like the biggest trick that can come out of factoring, and I'm putting it here right at the very beginning of the course because this will come back to get you if you don't pay attention to this right now. See this one? That can be factored even more. So we have to actually, when we say factor fully, it means we need to break down each expression into the simplest parts that they could possibly be. So this, of course, is a difference of squares, and we can write this as a minus b, a plus b. This is just the classic difference of squares. And of course we keep our a squared plus b squared. And this is the fully factored form. I can't do anything with a squared plus b squared. And a minus b and a plus b are linear monomials. So you can't break them down any further. Yeah, that's what I want to cover with that one. Okay. So the next example we're going to be expanding, and this is really just a review of how to expand things. Maybe the technique that I'm going to show you here is a little, it might be new to you. I find it helps a lot. Okay. So if you remember from grade 11, I don't know if they cover this in every grade 11 curriculum, but there's actually a trick for doing these. It's called Pascal's triangle. It's called the binomial theorem, and it involves Pascal's triangle. That is the triangle that has the numbers like this, and each level tells you the coefficients of the terms when you get a expression of this type. So if you remember Pascal's triangle and how to use the binomial theorem, after a bit of work, you could very quickly come up with this. X cubed plus 3x squared y times 3 plus 3 times x times 3 squared plus 3 squared is 27. Okay. And then simplifying this, you get x cubed plus 9x squared plus 27x plus 27. Okay. This is not the way I want to do this. I'm just saying this is like the quickest way of being able to do it. But we can do it a more dirty way, and that would be just expanding it using, you know, your FOIL approach. So really, x plus 3 cubed is x plus 3 times x plus 3 times x plus 3. So I'm going to multiply out one of these. So if I multiply out the first one, you can use FOIL or another trick that you know to get this, x squared plus to 6 x, sure that's right, yep, plus 9. And then we have to multiply this again by x plus 3. Okay, now this gets a little messy because there's so many terms here, and there's 2 terms here. So what I'd like to do is organize my information to a table, a multiplication table, if you will. So I'm going to write my first one, x squared, 6x, and 9 here. I'm making special attention to the signs, because the signs are what can get you if you don't do this carefully. So I make my multiplication table here, and then I multiply I just multiply the top and the side entries, and that's what I put in here. And at the end, all I have to do is add up all these entries, and then I'm done. So this is x cubed, this is 6x squared, this is 9x, this is 3x squared, this is 18x, and this is 27. If I went too fast, please go and try and do this yourself, and make sure you get the same numbers here. I don't think I made a mistake. Well, yeah, that looks good. Okay, and then you just have to add them all up. Like terms combine, so you get x cubed plus 9x squared plus 27x plus 27, which of course is the exact same thing as we got up here, which is good. We would be in really big trouble if they were not the same. Okay. My next example is going to look very similar to the first one. It's going to be a to the 4 plus b to the 4. So try and factor this for yourself, see if you can get anything. And I hope you came up with absolutely nothing, because you cannot factor this. Yeah, this is a trick. So if you're given something that you know you can't factor, or you can't think of any way of factoring, it's probably because you can't factor it. You should probably just run through a checklist of things to make sure that you haven't missed anything. But if you've spent like 5 minutes trying to think of ways to factor this thing and nothing's come up, it's safe to say this thing's not factorable. And maybe it's good to note other things that aren't factorable include expressions like a squared plus b squared. You can't factor that anyway. However, and this is the big however, you can factor this. A cubed plus b cubed. Sorry. No, you cannot factor this. And maybe this is a good time to bring up again the issue that a lot of people have. This thing here, a squared plus b squared, is often confused with its bracketed counterpart, a plus b squared. Okay, this you can break down, of course, into a squared plus 2ab plus b squared. Please do not ever mistake these two as being the same. They are, as I've just shown here, they are not the same. Okay, so the next example is another expanding. We're going to do x to the 4 plus 3 times x squared minus 1. Okay. Now you can FOIL. You can go ahead and try this yourself. The only reason why I have this here is that you remember your exponent rules. So when you multiply x to the 4 and x squared, you're not multiplying the exponents, you're adding the exponents. So the result here is going to be x to the 6, and then you're going to, if you do FOIL, I guess you do first, and then, sorry, I just never use FOIL myself, so it's hard for me to try and get it back on the fly, but that's what you should end up with. So it shouldn't be too difficult, should be familiar from grade 11. But this next one, I've designed to try and trick you. This one is going to be, just switch to a different color. T to the negative 1/2 plus 2 times t to the negative 1/2 plus t to the 1/2. And wow, that looks absolutely horrible. Yeah, it is. So let's just go through this slowly. We'll FOIL it together. So we take the first ones, okay, And remember, when we're multiplying these two terms that have the same base, you just add their exponents together. Negative half plus negative half is negative 1. So this just becomes t to the negative 1. Then we do the outer ones. Okay, well, what's t to the negative half times t to the half? Again, we just add their exponents together. But if you add them, you realize you get 0. Okay, well, what is t to the 0? It should be a well-known fact to you by now that anything to the power of 0 is just 1. So actually here, where we had two t's to the something power, we just get 1. Okay, so that's a little unusual. Okay, next we'll do the inner ones. So 2 times t to the negative 1/2, and then we'll do the outer ones. Okay, really the only tricky part here is that. Okay, the rest of it just goes as a regular foiling, expanding problem. Okay, but I just wanted to point that out because it's an easy mistake to make. You get lost and you start losing track of things, and it all just goes downhill from there. Okay. Okay. So my next example is going to be going back to factoring. I think in grade 11 they sort of beat it into you to factor not only expressions that fit on one line, but also rational expressions. So expressions with a top and a bottom. So we're going to do a couple of those. All right. So the first one I have here is x squared minus 1 over x plus 1 times x plus 3. I'd like for you to try and do this one on your own. It should be okay with the knowledge that you have from grade 11. In the meantime, I'll just write another one up here. This one you can also try on your own. And just one more over here. Okay. So let's go through each of these. If you haven't paused the video, I would encourage you to do so now and try to do each of these on your own. Get yourself an answer, and then just see where see if our solutions match, and if they don't, where they differ. Okay. So I look at this one, and the first thing I see is a difference of squares on the top. So I'm going to go ahead and break that up into the two bracketed parts. It's almost always a good idea when you see something like this to try and make the expression that does not have brackets into something that does have brackets. It just makes it a lot easier. And always be on the lookout for two things summed and then squared, or difference of squares. Those are the two most common factoring tricks that people will try and bring up against you. Okay. So here, we're going to go ahead and break this up into x minus 1, x plus 1, all that over x plus 1, x plus 3. Okay. The x plus 1 here matches with the x plus 1 here, so we're going to cross both of these out. Okay. And that just leaves us with x minus 1 over x plus 3. Notice that I can't cross out the x's. This is a very bad thing to do. Please never do this. Next example, let's see, what can we do? So the top has already been factored for us. We can't really break x plus 1 and x plus 2 any more than they already have been. So let's see what we can do with the bottom, because right now nothing's going to cancel. Okay. Well, the bottom is a quadratic, and you know that you can factor quadratics. A lot of the time it does not work very well, but sometimes you can just look at it and find some way of factoring it. So I don't know what tools you have from grade 10 that allow you to factor quadratics, but you should be familiar enough by now that you can look at this, and if I told you to factor it, you can factor it. The only thing that is not said in the question is that you do have to factor it. So that's a little tricky. You need to know to actually factor it in order to be able to solve this question completely. So let's just go ahead and factor it. This becomes x plus 2 and x plus 1. Just quickly double checking. The 2x and then the 1x combine to make 3x, and then the 2 and the 1 combine to make a 2. We're done. Okay. I'll bring in the numerator now. X plus 1 squared, x plus 2 cubed. Okay, and we notice, okay, so there's an x plus 2 here and an x plus 2 here, and there's an x plus 1 here and an x plus 1 here. So we're going to have to cross some things out. We can take out an x plus 1 and take off one factor of x plus 1. So we're still going to have one x plus 1 in the numerator. Same thing goes in the denominator. So we're going to take off an x plus 2, and this 3 is going to become a 2. We can only take off one factor of x plus 2. What does this leave us with? Well, it leaves us with x plus 1 times x plus 2 squared. And this is as simple as we can get it. Now, notice when we ask you to simplify our factor, you don't have to expand it all over at the end. Right? There's really nothing much that you can do here. And this is something important to keep in mind. Later on in the course, we're going to find a way to simplify these expressions. Really, all we're doing is going to be writing it in a different way, but it's important when you're given these simplify or factor or expand questions to know exactly what you're doing so that you don't do more work than is necessary. So here's an example where you really just need to stop after this and just like put your pencil down and stop doing stuff. If you try and expand it, you're wasting your time. You're not doing what the question asks you to do. Okay, this one, a little tricky, and your first instinct might have been to try and factor this one. In which case, what would you have come up with? Let's see. Well, I believe you come up with 2x plus 4, and then there's another 2x plus 1, I believe. No, it's 2, I think. I think that's right. No, this, let's see. This gives me a 4x squared. That gives me, I think I need a 2 here. No, an 8 and a 1. What do I do here? No, you can't. Sneaky boy. Alright, on to this one now. So the first thing that you might have tried when looking at this is factoring out this bottom thing. You would have been unsuccessful because you can't factor it. But there is one thing that you should notice, which is that everything here is divisible by 2. So I want to pull out a 2 from here. Let me just switch pens. I want to pull out a 2 from here. That gets me 2 times x plus 2. Okay. Inspired by that, you may notice that the bottom also has 2's everywhere, factors of 2's everywhere. So I can do the same thing. I can pull out another 2, and I'm left with 2x squared plus x plus 4. And if you didn't believe me the first time when I said you couldn't factor this 4x squared plus 2x plus 8, you definitely can't factor this one. I'm really not sure how to make that sound obvious, but you can go ahead and give it a try, and it's not going to work. And then that is pretty much all you have to do for this. Just make sure that you don't try and invent some sort of factoring just because you desperately want this x plus 2 here to be cancelled. It's okay for it to be remaining there. You'd be doing yourself a disservice if you invented a factoring for this. Okay? It's never good to invent math unless you know what you're doing. Okay, next one. And this is the last example that we're going to do of this type, and then we're going to move on to learning some new stuff. So we have the square root of x plus 3 times the square root of x minus 1. All of that over x squared plus 2x minus 3. Okay, this one might look a little bit daunting at first. So let's just take it slow. The one key point I want to emphasize here is that whenever you have a square root of something, that's the same thing Let me just write it in the corner here. Square root of x is the same thing as x to the 1/2. So really what I'm going to do is I'm going to replace all these square roots with halves. It doesn't change the question a single bit. That's the definition of square root, by the way. It's the 1/2 power. Now you look at the bottom and you're wondering, maybe I can factor it. Try, and you'll find that you get x plus 3 times x minus 1. Oh, great. Okay, so what this shows us is that, hey, look, there's some similar stuff here, and there's some similar stuff here that we can try and cancel out. Okay, let me just make it a little bit easier to see by putting the 1s over here. Usually we don't put the 1s because it's redundant, but I'm going to put them here just for today. And what I want you to see is that these two expressions have the same base. That's an x plus 3. That's an x plus 3 up here. And when you're dividing two expressions with the same base and have an exponent, you just have to subtract the exponents. So all we're left with here is an x plus 3 to the negative 1/2. In a similar way, I could do this one. This would give us x minus 1 to the negative 1/2. Okay? The last thing you might want to do is, well, because these two are both under the same power, you can sort of like combine them all together. So I could write it as x plus 3 times x minus 1, all of this to the negative 1/2 power. And then I'm done. I'm not going to break this up any further. It won't actually make it any simpler. I've done everything I've had to. One could even argue that even this step, going from here to here, is redundant. Again, this is all teacher preference. If you ask me, I don't mind, but there are some people who will be picky about this, so you just have to be cognizant of that in the fall term. Okay? All right, so now we've done enough of that to get a good feel of it. We're gonna sort of stretch the bounds on what you know about factoring and introduce two new elements, not to make it harder, but to make your future self have an easier time solving problems that will implicitly involve factoring and expanding. Okay? So the first one is this: rationalizing denominators. Okay? And here's the setup. We basically have an algebraic expression, an expression meaning doesn't have an equal sign. So it's something like 1 over root 6. Okay? No variables today. At least not yet. And just looking at it, I've written it like a fraction. Okay? But the problem is, what is root 6? Does anyone count on their fingers root 6? I go 1, 2, 3, 4, 5, root 6. It doesn't work like that. Fractions are meant to be intuitive things, and having a square root in the bottom is not a very intuitive thing. So we would like to change that. At least make it so that the bottom thing is not a radical. So we want it to basically de-radicalize this this denominator, and that's what rationalizing means. Okay, you're taking out the radical. And in order to do this, I'm going to bring up one important fact, which is this. Suppose I have root x. Okay. How do I get x? I just have to multiply by another root x. And to see this, well, root x and root x, that's just x to the 1/2 times x to the 1/2. And by your basic exponent laws, you know, you just add the exponents and you get x to the 1, which is x. Okay? So maybe we can try the same thing here, except we got a problem. And that problem is, I can't just change my expression at will. It's against the rules. So that sucks. However, there's one last thing that you might want to try, which is multiply by a clever form of 1. And what this clever form of 1 is going to do is it's going to utilize this property, and it's also going to get what we want out of here, which is getting rid of the square root. So you may already be thinking to yourself, well, it's obvious now. I just have to multiply root 6 over root 6. And you'd be totally correct. Because once you do this, what do you get? You get root 6 over 6. The root 6 times root 6 just gives you 6 by this rule over here. And now we've successfully changed our expression. I don't know how happy you feel about it. Really, all it looks like we've done is move the 6 up, the radical up to the numerator. But, you know, for a lot of things that we do in math, this is actually a more helpful form, and it's a more useful form because now we have a actual integer in the bottom, and we know what integers mean. I can count up to 6 in my fingers. So that's the premise of rationalizing the denominator. Let's see it in a more complex setting. So here, what we have is an expression, x minus 1 over square root of x plus 3. Okay, and I want to rationalize the denominator. Okay, so how I'm going to do that is basically apply the same approach. I'm going to try and get rid of all root signs in the denominator just by multiplying by clever forms of 1. So let's do that. Obviously, if we multiply by root x plus 3 over root x plus 3, we'll get rid of the square root. That's just by our simple law that we had on the corner earlier. Okay. So I multiply these two out. What does it give me? On the bottom, it just gives me x plus 3. And on the top, well, there's nothing really that you can do, so don't try and do anything. Just go with the flow. I put brackets just to make it a little bit more clear, because if I didn't put brackets, then we would have, what, x minus 1 times x plus root 3. And it becomes a little bit ambiguous, like what do you mean? Do you mean x minus x plus 3, or do you mean x minus 1 times root x plus 3? So brackets always for security. So the next example that I want to go through is one that will be very useful in the next course, but it's worthwhile to go through this example just because it illuminates one of the more difficult aspects of rationalizing the denominator. So far we've dealt with some simple examples that only require you to multiply by a clever form of 1. This example is no different, but the clever form of 1 is a little more subtle. So the example is this: 1 over root x plus root a. Okay? And so what we want to do, again, in rationalizing the denominator is get rid of the square roots. But now we have a problem. Whereas before, these two were multiplied together, now we have an addition sign. We can't simply just multiply by root x plus root a. It doesn't work this time. And to make sure that you understand why it doesn't work, we're just going to multiply it out quickly in the table. So root x plus root a, root x plus root a. Okay? And if you multiply these two together, you get x. You multiply these two together, you get root ax. You multiply these two together, you get root ax again. And you multiply these two together, you get a. And that gives you x plus 2 root ax plus a. So if we did multiply by root x plus a over root x plus a, root x plus root a over root x plus root a, then we would get this. We would get this in the denominator. We still have a radical here, and this is a bad thing. We don't want this. So we're going to have to change our approach this time and use something a little more clever. And I want you to think about what clever thing we might multiply root x plus root a by in order to get rid of the root here and the root here. There's actually one thing that you can multiply, and the result, I'll just tell you immediately, is, so again, we multiply by some expression here that is a clever form of 1, so we have the same thing in the top and the same thing in the bottom. And the end result, I'm going to tell you now, will have a denominator that is x minus a. It's a little strange because there's a plus sign here, but there's actually something very clever that you can multiply by that will give you a minus sign here. So pause the video, try and think about it for yourself. And the answer actually goes back to difference of squares. The thing that you want to multiply by is root x minus root a over root x minus root a. What happens now is if you consider the bottom, remember when you're multiplying fractions, the numerator multiplies with the numerator and the denominator multiplies with the denominator. So what happens now when we multiply these two, we actually get a formula that resembles the difference of squares. Except now we have that this thing is equal to root x squared minus root a squared. The square and the square root cancel out, and this gives you x minus a. So make sure you really understand this because this is an important idea and it's going to get used a lot this term and the next term. Okay? So all this means is that when we multiply it out, we rationalize the denominator, there's no more radical up here, and the radical gets shifted up to the top, we get root x minus root a. And that is our answer. Okay? So study this example well, very important. Definitely will show up in homework. Okay? Alright. Okay, the last thing that I want to do is introduce something called the difference and sum of cubes. Okay, and this is something that we're going to use a lot for this course and for calculus. It's a really useful tool, and it's actually a better thing if you try it out yourself rather than me tell you exactly how to do it. So what I'm going to do is I'm going to present to you the formula, and then I'm going to ask you to verify the formula and make sure that you understand why it works. But when you're actually doing it in the real term, you won't have to do this every time. I expect you to just memorize the formula and be able to pull this out on the fly. But at least for when you're learning it, you should understand why it's true. So here we go. The first formula is this. X cubed plus a cubed is equal to x plus a times x squared minus xa plus y squared plus a squared. Okay? Now you may be wondering, how on earth am I going to remember this? Well, let's put aside that question for now. I'll show you the next formula in just a second. But the thing I want to point out is that this formula is extremely useful. You can see that's extremely useful because it takes something that doesn't immediately look like you could factor it and factors it. It factors it into something like this, right? And depending on what x and a are, if a is just a number, this thing might end up being a quadratic. Okay? So just be on the lookout for that. It's a very convenient form to have. Okay. The next one is x cubed minus a cubed. And this, it's going to look similar, but it's not the same. Okay? So here's how you're going to remember these two formulas. Okay? It's called SOAP. S-O-A-P. Okay? What this means, SOAP, stands for the signs that you're going to add into each of these forms. So what this means is that you need to remember the form. You need to remember that it looks like x something a times x squared something xa something a squared. Okay? This is what you really need to remember. SOAP will tell you what to fill in for each of these. Okay? For each of these blanks. Okay? Now you see there's 4 letters here and there's 3 spaces here. Why is that? Well, it's because AP is one thing. I don't know who came up with this, but it seems to work with most people. So we're gonna go with it and see if it works as well. Okay? So S stands for same. O stands for opposite. And AP stands for always positive. Okay? Now what the heck does that mean? So what you do is that when you want to find out what is x cubed plus a cubed, you put in the first position the same sign. So if this was a plus, you put in a plus. Okay? So let's just retry this. I'm going to erase these. So let's just try rewriting these using this SOAP formula. So we know that our thing has to look like this. I'm just copying down what's over there. Okay. We know our form has to look like this. Okay, so if we put the same sign, that's a plus. So we'll put a plus here. Then we'll put the opposite sign. So the opposite of a plus is a minus. So we'll put the opposite sign. And then the last one is always positive. So we'll put a plus. You can rewind the video and check that this is the exact same formula that we had to begin with, right? So now try using this formula to write down x cubed minus a cubed in its factored form. Just pause the video right now and try it yourself to use this rule, and see if you get the following: x minus a, x squared plus ax plus a squared. So again, same sign, opposite sign, always positive. Okay, it's not that hard. The only tricky thing is you need to remember the form. Okay, but we're going to do a lot of these, and it's going to show up so much in the polynomial section that you'll be forced to remember it. Okay, now there's only one last thing that I want you to do. Just to reiterate, I said at the beginning, and I'm going to say it again, I don't want you to just accept this. I want you to actually go and prove it. So exercise for you to do either now or at the end of this video, which is going to end very soon, exercise is to prove both formulas. Okay? And in case you don't know how to prove it, all you have to do is multiply this thing out and show that's the exact same thing as this, and do the same thing for the second one. Okay? If you're really comfortable with your expanding and factoring, you don't need to do both, but if you're having a little bit of trouble, like let's say you made a mistake doing the first one, I would recommend that you go through both and make sure that you can do them well. It's a good exercise in expanding and factoring. Okay, so once you've proven both formulas, now it's time to actually put these into practice. So here is a example, two illuminating examples that will be very useful and are actually quite tricky. Okay, the exercise is to factor fully again. So we're going to factor fully x to the 6 minus y to the 6. Okay, now let me tell you why this is a good exercise. Because 6 is 2 times 3. When I break this thing down, when I'm going to factor it, I'm going to be left with x to the power of 2's and y to the power of 3's, and x to the power of 3's and y to the power of 2's. Okay? What this means is that it's going to involve difference of squares, it's going to involve sums of squares, it's going to involve difference of cubes, potentially even sums of cubes. So what you have to do now is make a decision. What do I want to do first? Do I want to do the difference of squares, or do I want to do the difference of cubes? Okay, so that's a decision you have to make. If that doesn't make sense, we'll walk through it right now. But what I want you to do is brainstorm. Just brainstorm. Don't spend too long on it, maybe like 20 seconds. Pause the video and think about how you would tackle something like this, factoring it fully. Okay, so hopefully you've given it a shot. One thing that you should probably notice by now is that x to the 6 is nothing but x cubed squared, right? And now you know that when that because of the laws of exponentiation, you can actually switch these two around and it doesn't actually change anything. So this is the same thing as x squared cubed. Similarly, y to the 6 is y cubed squared, which is the same thing as y squared cubed. So this is the decision that I was alluding to earlier. You can either view x to the 6 and y to the 6 as this first thing, or you can view it as the second thing. And depending on your choice, that's going to influence what your solution will look like. But at the very end, both should be the same. That's the beauty about factoring. There's only one right answer. So here we go. I'm going to do it first this way, and then I'm going to do it the second way and show you that you get the same thing. Okay? So the first way, I'm going to reinterpret this question as saying, okay, I'm going to do it here, x cubed squared minus y cubed squared. Okay? And what do I see here? This is a difference of squares. So that means I have to apply the difference of squares formula. What's the difference of squares formula again? When I get x squared minus a squared, this is equal to x minus a, x plus a. Okay? Really, really bang this into your head, or else you're going to miss things like this. Okay? So now when I fill this in, I just have to substitute in my values. Of course, this x here is not the same x as there, so we'll just ignore that for now and just keep the idea in mind. So this is going to become x cubed minus y cubed times x cubed plus y cubed. Okay? Hopefully you can see how this formula just got applied directly to this. Okay? Now, what's the next thing? Well, the next thing is to see what can I do after this, right? So originally, before we started this this lecture, you may have thought that, oh, I'm done here. Well, now I've just shown you that you're actually not done here, right? There's actually more that you need to do. So what you're going to do is you're going to expand each of these. Okay, we're going to use the SOAP formula. Conveniently, I've written it right here, so it's actually, you don't really have to do much. You just have to copy them down and multiply it out. So just for the sake of doing it, here we go. I'll do this one first. So I'm just copying the formula that's up there. X minus y, x squared plus xy plus y squared, right? Because we're dealing with y and not a. And then you just multiply by the x cubed plus y cubed. Okay, and that's just x plus y times x squared minus xy plus y squared. Okay? Now, I want you to try it the other way. I want you to interpret this x to the 6 minus y to the 6 as a difference of cubes and see what that gives you. Okay, so try that out on your own first, and then we'll see if we get the same answers. Going to erase what's going on here. Yeah. So as you notice, I'm telling you to do a lot of things on your own during the lecture. The goal is that I don't have to spell out everything for you. That I can just give you some motivation, some idea of where this topic is heading, and that you can do the work on your own. This is going to help a lot for your exercises, because not only do you get to try them out on your first go at it, but also you get to see me work through the solution together with you. Okay, so now we're going to treat this as a difference of cubes. What we're going to do is we're going to rewrite this question as x squared cubed minus y squared cubed. Okay? Applying the difference of cubes formula here, what we're going to get is x squared minus y squared times, okay, so x squared, so we have to square this thing. So x squared squared is x to the 4. Okay? X to the 4 plus, okay, we have to multiply this a by the x, so we have to multiply y squared and x squared together. So that gives me x squared plus y, x squared y squared. And then the plus here. And the last one is y to the 4. For the exact same reason, this one was x to the 4. Okay? Now, the first thing that pops out to me is that this is a difference of squares. So let's go and expand that right away. This is x minus a, x plus a. If you didn't catch that immediately, you should really take this as a lesson, an opportunity to reinforce that this is the most devious trick that can come up in these factoring questions. So always be on the lookout for this, having a hidden difference of squares. Okay? Don't invent a difference of squares, but just be aware that it is something that will often pop up without, and it'll pop up with the teacher trying to make you not realize it. It'll be embedded as a step of the problem. Right? So now that we're entering grade 12, these factoring problems, they might not just have 1 or 2 steps, they might have 3 or 4. Okay? Now, the next thing that we want to do is see if we can do something with this. Okay? Now, it's not immediately obvious if you can do anything with this. So what you're going to do is you're going to look at our previous solution. So what was our previous solution again? Let me just remind you. It was x minus a times, it was this thing times this thing. I hope you can go back in the video and check. X squared plus ax plus a squared times, sorry, I'm blocking the board, I know. X plus a, x squared minus ax plus a squared. Okay. So you may be wondering why this does not look like this. The only thing that we haven't accounted for is this thing and that thing, right? So what we need to show now is that this part here is actually this multiplied by that. There's no obvious way to factor this. It's actually incredibly difficult to just look at this and know how to factor it, right? So all I'm going to do is show you that they are in fact the same, to show you that these two approaches do technically work, and then based on this, we're going to make a verdict on which of these approaches is actually better. So let's just make a table, and I'm going to multiply these two out and show you that it's the exact same thing as this. Okay? It's definitely not obvious, and I don't expect you to be able to do this, as in like be able to factor this thing into these two things. But just for an example, I'm just going to show you. So I'm going to make a table again. X squared, ax, a squared, x squared minus ax, a squared. Okay? If I multiply it out, you'll get x to the 4 here, ax cubed, x squared, a squared, minus ax cubed, minus a squared, x squared, minus a cubed x, a squared, x squared, a cubed x, and a to the 4. Okay? Just notice that these two cancel out, these two cancel out, these two cancel out, and you're left with x to the 4 plus a squared x squared plus a to the 4. Sorry, I should have had all these y's. Sorry about that. Yeah, so these are all y's. Okay. Sorry, yeah. But hopefully you get it. So just in short, if I multiply these two things together, I know I wrote a's there, but I really meant to write y's. I get x squared, x to the 4 plus x squared y squared plus y to the 4. And that's exactly what we have up there. So they are the same, it's just very, very difficult to see. Okay. Now, if you had gone this approach, you probably would have stopped here. It's very unreasonable to expect that you would be able to factor this. It's actually very difficult to see a factoring of this, especially as something as neat as this. Okay, but what this does go to show is that there was clearly a better method. Okay, and the better method was this first one here. Okay, so how do you remember which one's the better one? Okay, just like here's the important piece of wisdom. The difference of squares formula is very simple. Okay, it breaks your expression up into two simple things. This one is messy. You get a quadratic, and it's not even a nice quadratic. It's not a quadratic that you can immediately simplify further, right? This is a hit or miss. Okay, so always when you're given a choice between doing between expanding this as x cubed squared or minus y cubed squared, or y squared cubed, x squared cubed minus y squared cubed, you always want to choose this one, because the rule is, and here's the rule, nice things first. Okay? If you're taking notes, this is a good thing to note down, right? So if you're doing a factoring problem, always do the nicer thing first. Do the easiest thing that you can see, and if you get that out of the way first, you'll be sure to get the factoring in the lowest form possible. Okay? So that's all I wanted to do for today. Next time, we're going to start going back to functions, and we're going to cover some important properties of functions. And you'll see more of what I mean about that next time.